Welcome back to our series of solution and explanation to competitive coding. Today we are going to solve LeetCode question number 53, that is maximum subarray. Okay, so let me read the question first. So given an integer array nums, find the contiguous subarray consisting at least one number which has the largest sum and return its sum. So basically what the question is saying that we are given an array of integers, and we have to find the contiguous subarray which should at least contain one number, so that that subarray shouldn't be empty, and which has the largest sum and return its sum. Okay, so we have to find the subarray from the array given to us which has the largest sum. Okay, so this value of sum of elements should be the largest, and we have to return its sum. So like in our example 1, if this is our array, as like -2, 1, -3, 4, -1, 2, 1, and -5, 4. So we have to count the largest, we have to return the sum of the subarray that results in the largest sum. Okay, so in this array, like 4 -1, 2, and 1 returns to be the largest subarray, sum of, okay, sum largest sum of subarray. So this 4 -1, 2, 1 sum up to 6, and this is the largest sum we can find in our array, and this is the subarray of the same array, and it's not empty, so this is the correct answer. So we have to return the sum, that is 6. 4 -1 is 3, plus 2 is 5, plus 1 is 6. Okay, so this is our subarray which has the largest sum, and in example 2, we have only one element, and it is the largest sum of subarray because we don't have any other element. And in our example 3, we have to add up all the elements to get 23, because if we add these two elements we'll get 9, and if we add these two elements we'll get 15. So if we add these three elements we'll get 14. That will be smaller, but if we take this subarray and add to this subarray it will result in 23. So the largest subarray, the sum of, okay, so the largest sum of the subarray would, if we add all the elements of the array, and it would turn out to be 23. So let's go to our solution space to see it in more depth. So suppose this is our array. This is our example first from our question. So the brute force approach could be if we have to try all the subarrays and find the maximum of those subarrays. Suppose initially we have some max value. Okay, so initially we have when we are at this array, when we are at this position, and this is our max subarray. So suppose our max is initially something minus infinite, and so when we reach this 0th position, so our maximum value is like -2 at this time. But when we move forward and we add this to our subarray, then we found it that our maximum value would now increase from -2 to 1, then we -1. Okay, so we are update our maximum value to -1. Then we move forward and we see that by adding this to our subarray we get our maximum value, like our next value, to be -4, which is not greater than our maximum, so we don't update our maximum value. Then we move on and add this. Then we find that if this is -4 and this is +4, so our now maximum value is 0. So we update our maximum to from -1 to 0, because 0 is greater than -1. Then we add to then we move to this, and we find it would return -1 as maximum value. So we don't add this. So we don't update our max, and then when we move forward to this, it would return value as 1. So we update our 0 to 1, and when we move on and add this one, it would give us 2 as the maximum value. And when we move further, we found it is returning value as -3, so we don't update it. And when we move forward, it would give us value as 1, so we don't update our. So up till now our 2 is maximum subarray value, that is sum from here to here, something like, okay, up till here, like from 0th index to 6th index is our maximum sum. So we now keep on calculating we keep on adding and keep on calculating the maximum value for all the possible subarrays. Suppose we started from here and we found that our maximum is 1, so we don't update because we already have 2. We move to here and we found our maximum reduced to -2, and we move here, we are now maximum become +2, and we already have +2. We move to this and it will become +1. We move to this, it will become +3. So we update our maximum to +3. and we keep on doing. We found it here, it will become +4, and this would give us -1, and it would give us +3, so we already have +4. Now we do for this, and we found out that our 4 would be maximum starting from this index, and our 4 would still be maximum. But when we start from this at this position, we found that our maximum would be 6, so we update our maximum to 6, and we keep on doing for all the sub arrays that are possible in this array, and we found that our 6 is maximum value. So we can return our 6 as max. Okay, so the maximum sum of maximum subarray will be 6, and we can return our 6 as maximum value. So this approach would take us O of n square times to compute the maximum subarray. So to make it better, we can use some memory to reduce the time complexity from O of n to some better value. So let me remove this and use some memory to see if it could do some better for us. Okay, so okay, so this is our, suppose this is our like array, or this is our memory we are going to use. So what we can do is that to reduce our time from O of n square to O of n is that we can use memory of some size. Okay, so what we are going to do is we are keeping our max to this. Okay, so suppose we are on this position. So what we are going to do, because for zeroth position we don't have any choice, so it would be our subarray of whatever it is present in, whatever value is present in the zeroth index. But for from first position, what we can do is we can check if alone this element is maximum value, or the sum of this element plus this element is maximum. So the maximum of if alone this value, or the sum of this value plus previous value is. So this is our DP array, suppose. Okay, so this is our DP array. So we'll check if the alone this element, or the sum of this element plus the previous index in our DP array. If the sum of these two are greater, we'll put max of 2. Like if the element alone is greater, we'll consider it to be a great maximum, and we'll put it here. But if the sum of these two are greater, like the index, like the element at that present index and the element present in our DP array before that index. Okay, so we found that for this case, if we do a sum of these two, we'll get -1 as our value. But so alone this like value is greater, so we can put it here, and we don't include this -2 as in our subarray. So for this type, for this we have like 1 as greater value, so we don't have to consider this element in our subarray, so we cross it out. And then we move forward and check if alone this element is greater, or the sum of this and this is greater. So if we found that alone this is -3, but some of these two are like -2, so we consider max of these two, so we'll put -2 here. Okay, so again we move forward and we consider like alone this is greater, or the sum of these two is greater. So we found out that alone this is greater because the sum of these two is 2, and alone it is 4, so we put max of that, we put 4 here. And now moving forward, we found that this is alone not greater, so some of these two are greater, so we put our 3 here because some of these two is 3. And again, this alone is not greater because instead of the some of these two are greater, so we put a 5 here. And so alone this is not again it is not greater, so we put our sum of these two here, and we get 6 as here. And alone this is alone all again this alone is not greater, so some of these two are greater, that is 1, we put our 1 here. And again this alone is not greater, so we have to put a sum of these two, and it will become 5. And then we can see our maximum value is 6, and we can simply return our 6 to win as the maximum value. So by doing this, we reduce our time complexity from O of n squared to O of n. So this is the concept of given by one algorithm, and basically we don't have to use like all these O of n space, but like this algorithm reduce our time complexity from O of n squared to O of n, but it increases our space complexity from O of 1 to O of n. So we can reduce this also by the use of one algorithm. So what is that algorithm basically says? The algorithm is like Kadane's algorithm. This algorithm is here. It is like written like Kadane's algorithm says that local maximum at index I is the maximum of a of I and the sum of a of I plus local maximum. What it is trying to say, Suppose we do it in the reverse order, our brute force approach in reverse order. Suppose we are trying to calculate the like maximum subarray from the backside of the array. Okay, so if we try to calculate for this time, we have like 4 as our maximum subarray. But if we calculate add 4 to this -5, we get like -9 as our like -1 as our maximum. So we don't update our maximum, and when we move forward we get like it would become something of 0, and at this position it will become 1. 2, and at this position it will become 1, and at this position it would become 5. So if we do in backward fashion, what we have to find that, like in this case, suppose this is our arrays. Okay, so to calculate the like local max or the maximum value, suppose including all from here to here values, if we are going to calculate what would be the maximum, alone -1, or 1 and -4, or like 1 and -4 and 1 and 4 and -3, or 1 4 -3 or 1, or -1 4 -3 1 and -2. So we found out that our 3 is maximum. Okay, so we found that this local in this local subarray, are this portion or this subarray is returns the maximum result, that is -1 and 4. So when we move forward to calculate the maximum value for 2, then initially it is like alone 2 is maximum. Yeah, it is maximum. Or 2 and -1 are maximum. No, 2 and -1 are not maximum, because they results in -1, and 2 alone is maximum. Then when we move forward, like if we do 2 -1 and 4, then we get that, yeah, this one is maximum. So we get the maximum value, and when we move further, like keep on incrementing element in our subarray, we found that this is maximum. And what the Kadane's algorithm says is, because we have already calculated local max, like local max for -1, then we can use that local max, because if we keep on moving, like if we keep on moving, adding elements and keep on moving down and adding one more elements to our like subarray, we found that we won't be benefited, because we have already found it 3 as here. So this row could be considered as our like maximum local max for our 2, like this position element, to be the maximum value. Because if we keep on moving down or keep on adding elements, we won't get benefit, because we have already calculated that this is the maximum element. So we don't have to care about this adding all these elements in our subarray. So we can use directly from here that for our previous element, if this one is maximum, this subarray is maximum, -1 and 4. So we can simply use this -1 and 4 as our maximum subarray, and simply add 2 to 8, and if it is like greater, then we can use it simply. So this is what Kadane is used to say. So the other thing I want to say, that to reduce the space, is that in this case we are not using like the elements that are present. We are only using the element which is like present in the previous position. So we can use only one element to store this value, and we can reuse it, and then we can update it. So we don't have to use like an extra space to store our previous results. So let me code this so that you can get the clear picture of it. Okay, so initially we have to create like 2 variables, one local and one global maximum value. So I can say int, suppose a local max. Suppose this is our local max, and initially we assign it to some 0. Okay, so now let me make our global max. Okay, so I can say int global max. Okay, so it will be something like integer dot min course value. Okay, so now I can iterate over our array to check for the local and global maxes. Okay, for int I equals 0 and I is less than or nums.length. Okay, now I can do our I++. Okay, so now we'll update our local max with the maximum of like initial value, or the sum of the initial value and the previous value. Okay, so local max would be, okay, max of like nums of I, either nums of I or nums of I plus local max. Okay, so our local max would be updated accordingly, and we have to check if our global max is like if our local max exceeds the global max. Local max is greater than global. My bad. Global max. And if it exceeds, we have to make our update our global max. So we can do is global max is equals to local max. Local max. Okay, now we can return our global max. Okay, so we have to do return or return global max. Okay, so let me check if it works or not. It's supposed to work, and if everything is fine. Okay, so it did work. So let me check for one or two other test cases. Okay, second test case only one. So let me check if it works for this one. Yeah, it did work too. And the third test case is like this one. If this one works or not. Okay, so let me check it. Okay, this one works too. Now let me check for one of our generate test case for all the negative values. Like suppose if it is like -1 comma -2 comma, okay, it is done. My bad, I'm putting dots. -1 comma -2 comma -3. Suppose all are negative, so let me see if it works for negatives or not. So yeah, it did work for this one too. So let me submit our codes to check if it is optimal or not. So yeah, it is optimal. Like it says, it is 54.54% optimal. Though we use only single for loop and some other values. Let me submit it once again, so to check if it is stable or not. So yeah, it seems to be stable, so no matter how we submit our code. So hope you enjoy learning, and if you have a better solution, you can comment in the comment section below. And as always, thanks for watching.